Good evening. Can you hear me?
Yes, sir.
Okay. So we will do today is we'll quickly go through this, whatever is there in week 4. Only the important parts. Okay. So we are okay. Just one more minute and we'll start. Okay. So yeah. So what we will look at today is very quickly we'll recap what surfaces are, what are contours and gradients, right? So that is the first thing we'll do. And then we will study these 4 algorithms: gradient descent, mini batch gradient descent, momentum based gradient descent, and Nesterov accelerated gradient descent. Okay, so these 4 we will study. And there are few more things in the in week 4, right? So the learning rate schedule, and really there's something more. That part will not spend any time. You can, whatever is there in the lecture should be sufficient. Okay, so we'll spend more time on these 4 main algorithms and try to understand what issues they suffer from and the main formulas that you'll have to make note of. Okay, so that's the idea. So you have what is called a surface, right? So the surface here is some 3-dimensional, it's embedded in some 3-dimensional space. So if you have 2 variables x and y, then the surface of the function corresponding to that is going to be embedded in 3D space. Okay, so if in general, if you have say d variables, a function of d variables, then the surface that results from a function of d variables, that will be in rd plus 1. Okay, so that's how the geometry is going to work. So now if you, once you have a surface, you can ask what are the contours of this surface. So contours are also called level curves. So if you want to look at all the points on the xy plane where the function takes on a particular value, so that is what we call a contour. Okay, so can someone tell me what the contours will look like for this surface? What will it be? Will it be a plane? Will it be a line?
Sir, ring-like structures.
Yeah.
Yeah, it looked like rings. So a little more specific than that. So is what geometric object is it?
Slices.
Yeah, you'll have to slice the surface. But if you slice the surface, what will you get?
Intersecting points at that slice.
Right, but what are they called? So what are those points going to form? They are going to lie on a particular curve. What is that curve?
Parabola.
It's an ellipse, right? Because if you slice it parallel, if this 4 were to be 1, you will get a circle. So x square plus y square equal to something. Now if you have other coefficients other than 1, you will get ellipses, right? So you'll have to visualize this. Not very hard. So you have to slice it parallel to the XY plane. Okay. And as you increase the height of the plane, will you get bigger ellipses or smaller ellipses?
Bigger ellipses.
We get bigger ellipses, right? So these are the values. So in this case, I have plotted f of xy equal to 1, f of xy equal to 2, and f of xy equal to 3. So these are three contours corresponding to this surface. Now, so that is with regard to surfaces and contours. So you must know how to read a contour plot. So if the lines, if the consecutive lines are very close to each other, then what can you say about the surface? Is it, how steep is it? So if you have very close contour lines, what can you say about the steepness?
Less. It will
It's
be less.
gentle.
No, it is just too steep.
Yeah, it's very steep, right? So that's how you read that. And if you have, so in this direction, for instance, along which direction is the curve, is the surface steep, along x direction or y direction? Most, I mean, where is it steeper? In this
Y
case,
direction.
along the y direction, right? So that can also be inferred from the equation. So x square plus 4y square. So the 4 coefficient of y square in this case is 4. So that also points to the fact that it is steeper along y, but in general, you won't have access to the function, right? You will mostly have access to the contour plot only. So you'll have to know how to read the contour plot. Okay, so that is with regard to surfaces and contours. Perhaps the other term might be easier, level curves. So level curves is probably better because you are cutting it off at some level and you're looking at all points that fall on that level. Okay. So now we come to the gradient. So this is gradient of f. Okay. Is that correct? Is that this arrow is this gradient of f or is it something else? What do you think that arrow is pointing? So if I say this is equal to gradient of f at this point, am I correct or am I wrong?
But sir, it is not the steepest. It should be a slight more angle towards 0. Am I correct? No, it is a 90 degree, so it should be correct, sir. That I
Okay.
feel.
But it's not pointed in the direction of increment, right?
No, it's a decrement. Huh? Why should it go to increment?
Yeah. So therefore, what should this be? Is this gradient of f or is this something else?
Tangent.
No. So it should be the gradient, na? Because if I go mark it on the surface, then it is going down. So 0 is on the going down. So I am moving towards the 0. That's I pursue.
Okay. So what is the direction of the gradient telling you? Locally, it's telling you the direction of steepest ascent or descent.
Steepest descent.
Ascent.
No, right?
Ascent.
Steepest ascent, right? So see, the direction of the gradient is the direction in which you have steepest ascent. So that's why we have gradient descent, right? So what we need, why do we need gradient descent? Because we want to minimize a function, and therefore we descend in the. So we don't ascend in the direction of gradient. We go in the negative direction of the gradient. So
Okay.
think about it. The circles, as the circles become bigger, the value of the function increases. So if I go a small way in this direction, will my function increase or decrease? If I go in this direction, my function will decrease, right? So what is this? This is actually negative gradient.
Yeah.
Okay, so in this case, the gradient will actually point 180 degrees opposite. So it will be pointing in this direction. That is gradient. Now, what we are usually interested in is negative gradient, right? That's why I have drawn this. And what exactly is this? In this case, it is 2x comma 8y. So partial derivatives are 2x and 8y respectively. Okay. So what other thing should you note here in this graph? Something else that you have to make note of. This perpendicular sign, right? So the gradient is perpendicular to the contour at the point where you compute the gradient. Okay, so this is an important point. The gradient doesn't actually directly point to the minimum. Okay, so this is not the gradient. Okay, that's the direction in which globally, if you think about it, if I move in this direction, I'll straight away go to the minimum. Okay, if I choose the right step size. But then the gradient is not pointing there. So the gradient need not point in the direction of the minimum. So you have to keep that in mind. Second point that you have to notice, the gradient will always be perpendicular to the contours at the point where you would compute the gradient. Okay, meaning if you draw a tangent to the contour at the point, then the tangent and the gradient will be perpendicular to each other. Okay, so these are some points you'll have to keep in mind when you are studying the gradient. So that is surfaces, contours, and then gradients. Okay, so we'll make use of this local information called the gradient while optimizing functions, right?
Sir, so you are saying basically gradient means it is opposite to the minimum. It be actual gradient means it's opposite to the minimum.
So it's not, I wouldn't say opposite to the minimum. If you move in the direction of the gradient, your function's value will increase. So if you want your function's value to decrease, you'll have to move in the opposite direction of the gradient.
Okay, sir.
Okay, so that is so that is gradients. Now, if you look at where they are used, where were we? We were actually trying to solve an optimization problem, right? So minimize the loss function. So from a general function of two variables, now you or d variables, come to the loss, which is a function of some parameters of your network, right? So in this case, there are, let's say, d parameters. So this is how your surface. So you can visualize this as some kind of a surface, right? In d+1 dimensional space, this is some surface, and the variables here that are important are the weights. Okay, so you must not confuse this with x and y. So x and y, yes, x are features labels, right? So now they are constants as far as your optimization problem is concerned, right? In the case of optimizing this loss function, your variables are w1 to wd. Okay, and what exactly is this? So this, if you zoom in, this loss is strictly speaking a function of weights and the data points. So you have feature, vector, label, and then you have the predicted label. So the loss is made up of sum of losses, right? So you have n data points, then you have a loss term that each data point contributes to. So you are essentially looking at a sum of loss functions. That is what L is. So for regression, this is each Li, you already know what this is. So it's half yi hat minus yi square, and this is negative log of the predicted probability of the true class, right? This is cross entropy, and this is squared error, right? So far, I think you know all these things, right? Now we come to the first algorithm, which is that of gradient descent. Okay. So in gradient descent, what do we have to do? It's very simple, whatever we have just been speaking about. So once you have a weight vector at some point in the space at time step t, you move a small step in the negative direction of the gradient. Okay, so eta is the step size, and that will take you to the next iteration as far as the weights are concerned. Okay, so now, so far in other courses, wherever you have encountered gradient descent, we didn't pay too much attention to W naught. Okay, so in some courses we set W naught to be 0, and in some other courses we set W naught to be, I don't know, something else, right? But in the case of neural networks, you have to be very careful with the choice of the initial weight vectors. So how you initialize your network is very important. For one, you can't set W naught to be 0. Okay, so that is one thing. It's not just 0. you can't initialize all weights to be the same value. So that is also not allowed. So do you see what will happen if you do that? Why is that going to be a problem?
Weights after that would be negative.
Sorry?
Is it because the output then is almost as good as the sum of the inputs in a way?
Okay, so yeah, so what happens is, if all the weights are the same, so let's take one layer, right? So let's take 3 neurons. Let's say a hidden layer has 3 neurons, and all the weights that are leading into it is the same, right? They are all the same. So what would these 3 neurons compute? Would they compute different activations, or will they all be the same?
Same.
They'll all be the same, right?
Same.
So
Yeah.
your neurons are not learning anything different. All neurons are kind of degenerating into the same thing. Okay, they're computing the same value. And if you think about it, if you do back propagation, the weight updates will also be the same, because there is nothing to differentiate one neuron from the other. Okay, all the weights are the same. So the updates are also going to be the same. So your entire network will get updated in a very similar manner, right? Each weight. So it's a very dangerous idea to initialize all weights to be the same value, especially 0 should be avoided. Okay. So in practice, what they do is, the weights are chosen randomly. Okay, they are sampled from either a Gaussian distribution with 0 mean, some epsilon square variance, or it's sampled from a uniform distribution, minus epsilon to epsilon. Right? So this epsilon again is hyperparameter, and that's chosen. There are some heuristics to choose the variance of the weights. But then the point you have to take away is, the weights in a neural network are initialized randomly. Okay, they are not set to 0, and that's a non-trivial step. Okay, weight initialization is a non-trivial step in training neural networks. All right. So apart from that, you also have eta, so the learning rate, which is again not trivial. So you will have to try out different eta. So you have already seen learning rate schedules from the lectures. You could try that. There are also other techniques. One is called line search, where you have a few values of eta, and you kind of try to find out what's the best eta. Other approaches are also there. So you typically have eta to be 10 power something, right? So 10 power minus 3, 10 power minus 2. 10 power minus 3 is like a very common choice that you go for. Okay, so eta is a hyperparameter for training. So these are all things you have to keep in mind. Even though it's just simple slide, there are many things that you'll have to make note of. Okay. So that is gradient descent. Pictorially, what is happening, if you think about it, you are at some point in the weight space. So we are in the weight space. This whole thing is the weight space. Okay, and your gradient, the negative gradient, is pointing in this direction, and you take a step in that direction. So that will take you from WT to WT plus 1. Okay, some other point in the weight space, and then you continue the process. So here the gradient will be pointing in, the negative gradient will be pointing in this direction. So you make another step. So maybe you land up here, and then you go here, and then finally you will come here. Okay, some sequence of steps that will take you to the minimum. Okay, so this is gradient descent. Now, gradient descent is known to converge for what class of functions?
Convex function.
Convex functions, right? So this is what we have drawn here is a convex function. Okay, so this is some x square plus 4y square, right? It's a convex function. So convenient. But then our neural networks are also functions, right? At some level. So are they convex functions? They are not.
Yeah.
So they are not convex functions. They are in fact non-convex. So highly complex, right? A neural network's loss surface is going to be far more complicated than what you see here. So they are not convex. So you have to keep that factor also in play, right? So meaning gradient descent is not necessarily going to converge to the global optimum, because you never know, you don't even know where the global optimum is going to be. So there are going to be lots of local optimum. Okay, so that is one of the issues with gradient descent. So we'll look at that soon. So there are multiple issues. So I have highlighted 4 of them. So first one is that gradient computation is computationally expensive, meaning if you have a lot of data points, which is usually the case in deep learning, right? So if you take what is called the ImageNet data set, so it's a very popular data set that was very instrumental in the revival of neural networks and the birth of deep learning. So that has roughly 14 million images. Okay, so you are talking about millions of images that you'll have to train on, and yeah, so 1 second. Yeah, you have to train on millions of images. So meaning, if you want to compute the gradient, you have to compute the loss function on a million images and then take the gradient, right? So that is a summation over 1 million terms. This can be a lot. Okay, so what happens is that computing gradient itself is going to be a costly operation. So that's the first issue. Okay, issue number 1. What's the second issue? That's what I have been alluding to. This is the local minima, right? Now, it's a very curious thing, right? So if you start from here, if you initialize your weights here, where do you think you will end up? If you run gradient descent,
At
start.
the origin of this graph.
Yeah, you will kind of end up here. That's the origin, right? That's one local minimum. If you start here, you will probably cycle this way or curve this way and end up here. If you start here, then gradients will kind of lead you to this point. Okay, so the more local minima you have, more is the problem that you'll have to tackle, right? So you don't know where you will end up. This, thankfully, in the case of neural networks, turns out that even though you have a lot of local minima, the value of the function, right, the value of the loss is not too far away from the global minima. Apparently, this is what research shows. Okay, so this local minimum is not exactly a problem when it comes to neural networks, because all the competing local minima kind of perform similarly, and they are not too worse off when compared to the global minimum. Okay, so this is not exactly a problem, but you'll have to keep this in mind, that when your neural network, when you train a neural network and it converges, it has not converged to the global optimum. In all likelihood, it has converged to one of the many local optima. Okay, local minimum. Okay, that's the second point. So what's the third point? So the third point has to do with the geometry itself, right? So of the loss surface. So you have to visualize this. Now, what I've drawn is a particular feature of the loss landscape where there is large plateau, right? A plateau is like a very gently sloping surface, right? So you can see that there is some kind of a gentle slope downwards. And then you have what is called a cliff, right? In the cliff, there is a rapid descent. Okay, and at the bottom you have what is called a valley. So this valley has perhaps the lowest loss. Okay, and then the function again rises. So if you are somewhere here, if you start gradient descent somewhere here, what do you think your gradient is going to be?
Near to 0.
Yeah, it will be very close to 0, right? So the gradient will be roughly 0. It won't be exactly 0 because there is still some. There's a small component here, but then it's going to be pretty close to 0, right? So if you start gradient descent here, then in order to escape this plateau, it's going to take a very, very long time, right? So the progress will be snail's pace, it will be progressing. Okay, so that's an issue when you have these plateaus. Okay, and then you have cliffs, right? The problem with cliffs is that when you reach this point, and if you have a large learning rate, right, somewhat large, so you would have had a large learning rate so that you can reach till this point quickly. But then if you continue with that learning rate, what you will do is you will overshoot the cliff, right? And you will end up somewhere here. So once you end up here, your gradient will push you back. So you'll have to do a little more work and before you find the sweet spot that's here. Okay, so the issue of having a plateau is something we'll have to deal with. That is one geometric defect. The second one is what's called the valley, right? So if you zoom in onto this region, whatever we have been seeing so far, they are called valleys, right? So what is the problem with valleys? You have this problem of oscillations, right? So meaning if you start gradient descent here, okay, so the first iteration will take you to this point. The second iteration will take you to this point because remember the gradient always points in the direction perpendicular to the contour at that point, right? So it will go here, it will come here, it will go there, it will come there, right? So there are a lot of oscillations. Okay, so what is causing these oscillations? One is, okay, visually you can see that there are oscillations, but why do you think there are these oscillations? So you have to look at this function and tell me what aspect of this function is resulting in these oscillations.
Momentum.
Momentum we have not yet added, right? So we are yet to add momentum.
So
We are-
still it goes some distance, then it realize we have to go to right side, then it will go right.
okay, so we have not yet added the momentum term, right? We are still looking at vanilla gradient descent. Okay, so if you look at the gradient here, there are two components, right? There is some part of the gradient along the horizontal direction, some along the vertical direction. Which is more?
Vertical.
Vertical, right? So you can see this numerically also. You have an 8W2 here and a 2W1. So if you maybe start at say -1, right? Somewhere here, then the negative gradient will be minus. So it'll be 2,8, right? So there is like you move 2 units along this direction, but you move 8 units along this direction, right? So there is a big component of the gradient in the vertical direction, and there is only a small component along the horizontal direction. Okay, so as a result, what happens is you ideally want to go here, okay, but then you are forced to go multiple times up and down. The reason is the sensitivity of the function is higher in the y direction or vertical direction. Okay, so this is a problem that's going to arise, especially when you are looking at neural networks with multiple weights, right? So here we only have 2 weights. So the problem is acute even with just 2 weights. Now imagine a neural network that has like say million weights, right? So there are going to be directions where the gradient is very high in one component and the gradient is very small in some other component, right? So you're bound to have these kinds of valleys emerge, and in those valleys there are going to be these oscillations. Okay, so these oscillations, if you think about it, that is one problem. Okay, so what else is there? What other problem does gradient descent have? Can you think of anything else?
If we consider local minima, it takes time to reach the global minima. It becomes quite difficult to move from local minimum to global minimum.
Okay, but it doesn't know, right? So the algorithm doesn't know where the global minimum is, right? So it may never reach the global minimum, right? So that is common to all gradient based first order gradient based methods. All suffer from, their ability to converge to local minimum is there, but there's no guarantee about the global minimum. Okay, so the one other problem you have to notice, the learning rates are not adaptive, meaning they don't adapt to the direction in the weight space, right? So what do I mean by that? So if you look at this, you know that the gradient in the vertical direction is quite large, okay? So the gradient is itself doing the job of moving it closer to the minimum. Therefore, I don't need a very high learning rate in the vertical direction. Okay, whereas in the horizontal direction, I might take the help of a slightly larger learning rate. Okay, because I want this component also to be large. Okay, currently this component is large and this component is small. What I want is a learning rate which adapts to the direction in the weight space. So I don't want to move this much in the vertical direction. Maybe I just want to move this much. However, I don't want to move by only a small amount in the horizontal. I want to move little more. Okay. Currently, if you look at gradient descent alone, the learning rate is not adaptive. There's one learning rate eta for all directions. Okay. So this will be later fixed in week 5 when we study adaptive optimizers. So optimizers with adaptive learning rates. But for now, this also counts as a defect of gradient descent. Okay. So is this fine so far? Can we move to the next part? Okay, right. So these are 4 issues. We'll address the first issue, which is that of efficiency, right? So if you have a huge data set, you can't run gradient descent on it because that's computationally prohibitive. You'll have to do something, right? So what you do is you cut down the data set size, and meaning you don't delete anything, but then you only tackle a small collection of points at a time. Okay, and you call that small collection of points a batch. Okay, and you keep running gradient descent on these batches instead of the entire data set. So we'll quickly go through the steps of this algorithm. So what do you do first? You have the entire data set, you have n data points. And what you do is you shuffle the data set. Okay, this is a very important step. If you don't shuffle, you are going to end up with some problems. So I'll come back to this at the end of this slide. Okay, so you shuffle the data set and then you select some section of the data set, right? So of B examples, right? You call this B batch size. So you are going to keep doing this starting from the left. You will take a B section, another B section. So maybe this is the third set of B data points. You call that a batch. B is a batch size, okay? And what do? You compute the loss for this batch. So how is the loss computed? You just add the losses for the B samples that are present in this batch. Okay, this is the loss at time step t. What do you do with this loss? You just compute the gradient of this loss function. Okay, remember that this is not the entire loss. This is the loss only on B examples. Okay, so you compute that. That will be your gradient, and you now run gradient descent. Okay, so this is called mini batch gradient descent. So you are basically what you're trying to do is you are splitting the data into batches and you're processing each batch as though that is the entire data set. Okay, so these batches are going to be different from one iteration to the other. And when you pass through all the examples in your data set, that is called one epoch. So one epoch is when you pass through the entire data set once, meaning each data point will come in one batch exactly, right? So you kind of go through the entire data set, that is called one epoch. So how many? So in each batch you update parameters once. So how many times do the parameters get updated in a given epoch? how total number of parameter updates that happen in one epoch. Is there a formula for that using what?
N by B.
B. N by
Yeah,
B.
N by B, right? So you do N by B updates in one epoch. Okay, so that is what happens. Yeah, you have a question?
Yes, sir.
Yeah.
So what I was thinking is, let's say I have decreased the loss for a particular batch, but wouldn't it be possible that these weights would increase the loss for any other batch?
That's yeah, that's a good point. That could happen, but that won't happen consistently, right? So it won't happen that every batch behaves that way. See, if every batch behaves that way, then effectively you are increasing the loss overall, right? So what happens that we'll come to that point. Once I finish this slide, I will talk about other aspects of stochastic, the mini batch gradient descent. So you have the entire spectrum. So if B is equal to 1, that's typically called stochastic gradient descent. So stochastic gradient descent is sometimes interchangeably used with mini batch gradient descent. So originally what they meant by SGD was you process one example at a time. Okay, that's the extreme case of mini batch gradient descent where you compute the loss on just one example, one data point, and then you update the weight vector using the gradient of that particular data point. Okay, so that is, you will do n updates in one epoch itself instead of n by b. Where when b is equal to 1, you will do n updates. So that is extreme version. So that's also called an online algorithm because your data points are coming at you. You can actually use this in an online setting where data points are fed one at a time. Okay, so that is stochastic gradient descent. When b is equal to n, you fall back to yeah. So there is some noise coming from somewhere. Yeah. So so when n is equal to b is equal to n, you fall back onto gradient descent. Sometimes that is called batch gradient descent. Okay. So too many terminologies in our course. We will always refer to it as mini batch gradient descent, where b is something less than n. Okay, so that is what we will refer to as mini batch gradient descent, MBGD. And usually the values of b are chosen to be powers of 2. So there are some reasons for this that have to do with the hardware that is being used. Okay, so there is not really a software thing, more of a hardware thing, and how you push your data onto your GPUs and all that. Okay, so that is mini batch gradient descent, right? So now we'll come to some specifics. So how does it fix the computational issue? By considering the gradient of only a small set of training examples. So it fixes that part. And so that is the main reason for introducing this. But interestingly, it also not fixes, but it also has few other interesting properties. So one thing is, in every iteration, you are looking at a different subset of the data. Okay, so that subset of the data is kind of representative of the entire loss function. Okay, so the loss of a mini batch is going to be representative of the loss of the total loss, right? So if you try to minimize, so what are you trying to do here in this setup? You are actually trying to minimize this loss function. You're not trying to minimize the total loss. So this is a very important point. Your goal is to minimize capital L, okay, without any superscript. But what you end up doing in each iteration is you end up minimizing a subset of the loss on a subset of data points, right? So how do you view this? In every iteration, your loss function keeps changing. Okay, so as long as your batch is representative of the total of the entire data set, you can assume that you are going to roughly move in the correct direction. Okay, so this is the question that you asked. So if you are
Yes, yes.
So the idea is the batch is representative of the total data set. Therefore, if you minimize the batch loss, you are kind of minimizing the total loss. Okay, so that is one aspect. Now, interestingly, this is going to help you avoid local optima. So if you look at local minima, so these are local minima, right? Now this is the local minima for the total loss function. However, when you are doing mini batch gradient descent, you are not going to consider the total loss function. So what is a minimum for capital L need not be a minimum for L superscript T. Okay, so you might end up escaping these local minima. So that is one advantage. Okay, did everyone get this point?
Yes, sir.
Okay, so what is a
But
minimum?
sir, but it may happen that actually I am not avoiding the local minima, but actually I am always going to the local minima because of this randomness.
You are always going to the local minima, which
Means you are saying that this will avoid the local minima. Okay,
this might avoid.
may avoid the local
Yeah,
minima.
yeah,
So, is there any guarantee that it will avoid the local minima?
No, there are no guarantees. These are all heuristic arguments, right? So more of based on experiments and very naive arguments. It's very tough to exactly say that this is what will happen. Okay, these are all intuitive arguments, not backed by theory.
So I think I'm not clear on the intuition either for why it would avoid a local minima.
So
Could you
see,
go over that once again?
See, what is the idea is, this is the contour plot for capital L, okay, where you have say 1000 data points. This is the loss. This is the contour plot of the loss function when plotted on 1000 data points. So this is what you have to minimize, and maybe somewhere here is where you want to end up. Okay, that's where the global minimum is. Now, if you take a batch size of 100, what you're doing is you are only considering the loss function on 100 data points. Okay, so that loss function's contour is not going to look like this. Okay, as far as that loss function is concerned, this may not even be a local minimum. Right, so there is a possibility that you might escape getting trapped in this local minimum.
Right.
Okay.
But it's only a possibility, right?
It's only a possibility, yeah. So
there could be a possibility that we could end up in a worse local minima also.
Yeah. Well, thankfully, what happens is you're not considering the same 100 examples, right? So every time you are shuffling the data set, so that brings in some kind of a regularization. So every iteration you're looking at a different subset, and as long as the subset is representative of the total data set, you are going to move in the right direction. Okay, roughly.
Okay. So all of this is built upon the fact that we are shuffling the data first.
Yeah. So what will happen if you don't shuffle is a very interesting question. So if you don't shuffle, let's say, I'll give you one instance where you don't shuffle. Let's say, where is that? Assume for a moment that you don't shuffle, and these B data points happen to be data points that have label 0. Okay, they belong to class 0. So if you now run gradient descent, mini batch gradient descent for this batch, what will happen is you are pushing the weights in a direction so that your network performs well on data points belonging to class 0. Okay, but that's not what we want, right? So we don't want the network to perform well in discriminating class 0 from the rest of the classes. Maybe there are 9 other classes, right? So if there are 10 classes like MNIST, you want the network to be able to distinguish any class from any other class, right? So if all examples in a given batch happen to be from the same class, it becomes suboptimal in the sense that your network for this iteration is being trained only to perform well on a particular class. So that may be suboptimal as far as the real problem is concerned.
Okay, so through one epoch, we risk oscillating between different biases.
and not towards the optimal solution.
Yeah, so the shuffling happens once every epoch. Before every epoch starts, you shuffle,
Yeah.
and then so you keep going through the batches. Okay, so these are some very heuristic arguments regarding this mini batch gradient descent, right? So how it performs. Okay, so that is mini batch.
Excuse me, sir.
Yeah.
When we shuffle the same points may get into the second batch also, isn't it? Isn't it possible?
Sorry, same.
Some of the points.
So the way we shuffle, see, let's say there are 1,000 points, you shuffle it, and each batch typically is mutually exclusive, right? You choose mutually exclusive batches. So you
it should be mutually exclusive. In that way only we can shuffle it.
Right. So see, shuffling. So for instance, what I mean by shuffling is if you have x1, x2, right? So this is your original data set.
Okay.
And let's say there are x10. Okay, there are 10 data points. Now, if you shuffle them, you may end up with say x3, x1, say some order. Okay, so I'm just 3157. Let's say the last data point is x9. So what I'm saying is, so now if your batch size is 2, what will your first batch? Your first batch will be x3, x1. That will be your first batch. Second batch will be x5, x7.
Okay.
And last batch will be, let's say, x2, x9. So they'll all be exclusive batches.
So after all this means 5 epoch, no? Or only 1 epoch?
This is 1 epoch. So 1 epoch with batch size 2 means you will have to do 5 updates.
5 updates we will do. Likewise, again, when we do it, this combination may change. That means x1 and x5 may be there in a batch.
That can happen. So this is epoch 1. Epoch 2 might have say it might have x1, x2 itself, right? So it can happen.
Yeah. Okay. So in that way, all the 10 points will be represented in a shuffled way. Okay.
Yeah. So all the 10 passing through all the 10 data points makes it 1 epoch.
Okay. Okay, sir. Thank you.
Okay, so that is the idea of mini batch gradient descent, and this is the default algorithm that's used. This and along with Adam, right, which we'll study next week, are the algorithms that we use. Okay, so that is NBGD. Now, that was one issue that we tackled, right? The first issue, which is what was computationally expensive gradient descent, and kind of we address local minima also using that, but again we have already established this fact that local minima don't present that much of a problem for neural networks. So which brings us to these two issues. So what happens when you are in a region with a very gentle gentle gradient, and what happens if you are in a region where there are wild oscillations like valleys? So is there some method that will help us address these two drawbacks? So that is where momentum comes in. So this is momentum based gradient descent, right? So what you do is you keep accumulating the gradients in a vector called ut, right? So ut -1 is a history of accumulated gradients till time step t -1, and for time step t you are going to accumulate the latest gradient that you have at wt, right? Gradient of wt. And instead of moving in the negative direction of the gradient, you move in the negative direction of this accumulated gradient information ut. Okay, so that is the algorithm. So it's very simple to state. Now let's see what exactly happens. Some algebra, if you do, you will know what is happening. So this is ut. Ut is beta times previous momentum vector plus gradient, right? So you just expand it. So you expand it by recursively you expand it, right? You're unrolling this recursion. So this is t minus 1 becomes t minus 2 plus gradient t minus 1. So this becomes beta square ut minus 2 plus beta. No, you do this one more time, two more times. Keep doing this. So I've done this here. And what you end up with is this expression. So this will go and hit u minus 1. So remember that u minus 1 was 0. So this term will vanish. And what you are left with is just a collection of gradients from time step 0 to time step t weighted by beta, powers of beta. Okay, I've just taken that outside and written here. So this is some kind of inertia. So what do you mean by inertia? You have to go back to physics example of ball, say a ball rolling down the hill. It accumulates certain, so it has some inertia, and as it goes down the hill, it kind of accumulates more and more energy, right? Its velocity keeps on increasing. So some idea such as that is that parallel is what you see here. So you have the accumulated history of all the gradients. Okay, so this is your current gradient, but then it's not just some accumulation, it's a weighted accumulation. Okay, so what you're doing is you're averaging gradients across time steps. So this is, you can call this a weighted average, but it's not any weighted average, it's an exponentially weighted average, meaning the farther back you go back in time, the lesser the weight or importance that you assign to the gradient. Okay, so this is the current time step. So this gradient is obviously the most important to you, so you give that a weight of 1. But then in the previous step, time step, I moved in this direction roughly. So I give that some importance, beta. But if you keep going back, maybe 100 time steps back, my gradient was this one, right? Now, that is not so important to me now. Right? That's like ancient. So the weight for that is like beta power t. Beta is a fraction, remember. So beta power t will be a very negligible quantity. So this is
So
what
is beta fixed or is it variable too?
beta is fixed in the sense that it's not a learnable parameter, so it's a hyperparameter, but it's fixed. It's fixed before the learning begins. Okay, so this is what we call a weighted average. It's an exponentially weighted average. Sometimes it's also looked at as a moving window. So what do we mean by a moving window is, so after a particular point in the past, right, your beta power t minus something will become so small that you can roughly treat these as zeros. Okay, so the effective window of gradient history is only this much. And if you think about it, this is like a window that you keep moving to the right. So currently this is the window. After one time step, the window will move a bit to the right. After another time step, the window will move little more to the right. Okay, so this is also looked at as a moving window where you're only interested in the history, maybe say for the last 10 time steps. Okay, so the beta power 11, beta power 12 will be so small that they all can be effectively treated as zeros. Okay, so, yeah.
So is t another hyperparameter?
T, no, right? So t is your current time step. So
so I meant how many steps in the past we'd be considering, or is that infinite, and then since it's exponential, like you said?
Yeah, so that is implicit, right? So see, this unrolling that we have done is we have explicitly unrolled it, but in practice we don't do this, right? So we do this forward computation.
We accumulate it.
Yeah, we accumulate, and implicitly we can see that the farther back into the past you go, the smaller your contributions from the earlier gradients will be.
Okay, so every gradient that we've computed from the beginning is technically contributing to it, but increasingly less. So.
Exactly.
Okay, I think I've understood most of it, except for how the beta power t plus 1 subscript -1 disappears. You said something, right?
So that disappears because u -1 you initialize it as 0.
I see. Okay.
Okay, and therefore, so u1, so u0 is actually u0 is nothing but gradient of w at the beginning. So gradient of w0 is u0. So you want that. So you set u -1 to be 0.
Okay.
Okay, so that is the idea of this ut term, which is telling you historically, okay, this is the direction in which you have to move. Okay, so this is kind of, if you allow me to go, I will go in the direction of ut. Meaning, if you forget this part, right, what remains is the direction in which I'll be impelled to move. But now I have some more information, so I'm going to add that. All right, so if you go back to this part, right, if beta is 0, you will see that this degenerates to gradient descent. So this is just moving in the direction of the negative direction of the gradient if beta is 0. Okay, so you have to take note of that also. Okay, and usually beta is set to some value like 0.9. So again, that there is no theoretical justification for these things. Okay, you try it out and see that beta equal to 0.9 works. So a lot of optimization in deep learning is engineering. So there is kind of.
But sir, it's like in the cliff also UT will be increasing only. So how it will? How
Correct. Yeah, this doesn't solve the problem with the cliffs, right? This part, whatever we have seen so far, it only solves the problem when you are in a plateau. Okay, so yeah, that part it doesn't solve. Okay, so that's what we are going to see. Why does it solve the problem when it comes to a plateau like region where the gradient is almost flat, okay, 0. Right? So if you look at these regions, there's one assumption that we are going to make. That assumption is that roughly all the gradients are going to point in the same direction. Okay, so roughly all the gradients across the time steps are going to point in the same direction. This is sort of a useful, not such a bad assumption, because if you notice, if you're here, there is no change in this direction. So your roughly all gradients are going to point in the same direction. Okay, so that's a assumption that you're going to live with. So if you make that assumption, then what you can do is you can take the gradient of W common out of all these expressions, and this becomes a geometric sum. Okay, it's a geometric series inside, and you can approximate it as 1 by 1 minus beta. If you allow this to run to infinity, it's 1 by 1 minus beta. So roughly this is the value of ut. Okay, so now if you plug this into your momentum update rule, so remember that Wt plus 1 is Wt minus eta times ut. So it's eta times 1 by beta times gradient W. So that's what you get. And this is where the benefit really stands out. So what is eta by 1 minus beta? So it is kind of an effective learning rate. Remember that if you had beta as 0, if beta were to be 0, this is just gradient descent. You just move some distance in the negative direction of the gradient. If beta is 0, that's gradient descent. But if beta is, say, something like 0.9, 1 minus 0.9 is 0.1. So you move like 10 times that distance in the direction of the gradient. Meaning you move a considerable distance more. Okay, which is what we want. If you're in a plateau, you want to move more, right? You want to take larger steps. So that is guaranteed by the effective learning rate. So when you have momentum is going to push you forward and make you move or make you take larger strides in the direction that you desire. Okay, so that's the idea.
And what happens when it is not a plateau?
Good point. So if it's not a plateau, then this approximation is no longer valid. So the
right.
right? So the gradients are not necessarily going to point in the same direction. So that depends, right? We'll look at the next case where it's not a plateau, but it's a valley. Again, that's a special case. For other cases, it's a bit hard to comment on. Okay, so at least in the literature that I've seen so far, they've only discussed these two cases. Okay, so what happens if it's a valley? So in a valley, notice what will happen if you are in WT. If you just do gradient descent, you will go here. Okay, but you are if you're doing momentum based gradient descent, then you have an extra term beta ut minus 1, right? So you have to move in the negative direction of ut, remember. So the update rule is what? This is the update rule, right? So minus eta times ut. So what we are doing is we are moving in the direction minus gradient of wt minus beta ut minus 1. Okay, so it's like two minuses here. That's what I've written here as minus beta ut minus 1 minus grad w. Okay, so you have to add these two. That's the effective direction in which you are moving. So if you add them, notice what happens. There is a component in this direction, vertical component, that's going to get cancelled with a vertical component in this direction. Okay, not completely cancelled out, but it will be dampened. So the oscillations in the vertical direction are going to get dampened, and the components in the horizontal direction will get amplified. Okay, so that will accentuate the horizontal movement, which is what you desired, right? So you wanted this oscillation to come down and this movement to increase. Okay, that's what momentum will do in the case of valleys.
Sir, I don't get it. How it cancelling the vertical movement?
Because you're adding these two vectors, right? You're adding these two vectors, and there is a component here and there's a component in this direction. So they are opposite vectors, right? So that part will cancel out to some extent. Right?
Okay.
So that is the idea. So if you actually look at, this is directly from Bishop. So if you look at these two graphs, do you see which one is vanilla gradient descent and which one is momentum based gradient descent?
Bottom one is the momentum based gradient.
Below, yeah.
Yeah, so the bottom one is momentum GD, the left one on the top is vanilla GD, right? So the idea is you dampening oscillations and fast tracking this movement helps it converge in fewer iterations compared to vanilla gradient descent. Okay, so this is two issues that we have somewhat addressed using momentum GD.
So just a moment.
Yeah.
This may be nitpicky, but since there is going to be another added component during each update, that means that we are no longer moving purely in the direction of the steepest descent, right?
Right.
So does that mean that as we reach, say, the global minima, is there a chance that we will overshoot or always just be slightly astray and not reach the pure minima?
That might happen, but you must also remember that when you get very close to the minimum, your gradients are going to be very small.
Okay.
Right? So the effect is not going to be that pronounced, right? You're going to be pretty close to the local minimum. So the gradient values are themselves going to be vanishingly small.
Right.
So once
that's good enough.
Yeah.
Okay.
Okay, so that is momentum based gradient descent. For this Nesterov, I don't have much by way of intuition. There is just one given in the lectures, right, where you look before you leap, right? That's what the prof says, where you already know that you are moving in this direction given by negative ut, right? So there is some momentum gathered. So instead of making the update first, you kind of see how your gradient is going to look like from the new position. So you first move in move by beta ut minus 1, negative beta ut minus 1, you go there, compute the gradient, and then accumulate that gradient, right? So earlier we were just doing gradient WT, but then now what we realize is I anyway know that there is some momentum accumulated. So let me go there, compute the gradient, and then accumulate that gradient to UT. Okay, so that's apparently that speeds things up. But if you look at the textbooks that I've shared, they also don't have much to say with regard to Nestrov. So that is all they have to say. This is anyway a comparison of all three, just to give you a sense of how they differ when it comes to the update. Okay, this won't give you the intuition as to why one is better, or so that part it won't give you. It'll at least summarize what is happening in each of these three algorithms. So yeah, you start with WT, and the gradient is pointing in this direction, negative gradient. So you make a step in that direction. So that becomes WT plus 1 for gradient descent. Okay, this is the WT plus 1 for gradient descent. Now for momentum, what happens is, let's say the momentum tells you that this is the direction in which the accumulated gradients lie. Now what you have to do, if you want a momentum update, what would you have to do with these two vectors? Can you see what you have to do with these two these two vectors? If you have to do a momentum based update,
Add them.
you have to add them. Yeah, you have to add them. If you add them, you will end up with this one, right? So you have to move from here to here. So that's the, so this is WT plus 1 for momentum gradient descent. So how will NAG look like? That I should draw one more vector. What vector will I draw here? Remember what NAG does? It doesn't compute the gradient.
It will be resultant vector of WT plus 1 and beta U2 minus 1. There will be a resultant, and that resultant I need to plus or minus.
Right, yeah, but not of WT plus 1, right? Of WT itself.
Okay.
See, this is WT. Now what you're saying in NAG is, okay, let me use the information I have and move in this direction first, okay? And look at the gradient there. So what I'll do is, I will go here, compute the gradient here. That gradient is this, so that is pointing in this direction. Okay, and now the update that I take is whatever history plus whatever gradient information I have here. So that will be my WT plus 1 NAG. So in terms of equations, if you go back, this is what the equation said, right? So you are having beta ut minus 1. So you are at WT, right? So you first move by beta ut minus 1. Okay, minus beta ut minus 1. Compute the gradient there and then add it to beta ut minus 1. So you have this, you move by minus beta ut minus 1. Okay, compute the gradient there and then add that to this quantity again. That will take you to NAG.
Can you go to the previous picture, sir?
So it's a question of where you compute the gradient, right? So in SGD, sorry, in momentum GD, you are computing the gradient first, correct? So you are computing this first. So this happens first. And then you are accumulating this direction, you're adding this existing direction and your gradient direction. So in both NAG and momentum, this is there. This is a fixed thing. The question is where you compute the gradient. In the case of momentum, you compute the gradient first in your current location. In the case of nag, what you do is you compute the gradient slightly ahead, right? So you look ahead. That's what the look ahead means, right? You look ahead based on whatever momentum tells you. You are looking ahead, and then you are making a little more conservative estimate of your gradient. This is that, and you are adding that to your existing momentum term.
And what do we gain from doing this?
That is something I'm also not sure. So see, the explanation given in the lecture, so that is what if I recall correctly, there's a different kind of oscillation that is being spoken of in the lectures. But yeah, if I looked at 2 textbooks for coming up with all this material, right? And both of them do not really talk about how nag is better. Okay, so I'm also not sure. I don't know what this does, what gains this gives, but yeah.
So probably it will give the less oscillation.
Yeah, but see, the point is the oscillations mentioned in the lectures are slightly different from the oscillations that are spoken of in literature, right? So they're kind of different. And see, the other problem is we are reasoning with images plots in 2D, right? With just two weights at the most. Even this plot, right? It's all good when it is in 2 dimensions, but your actual neural network is in like a million dimensions, right? The loss surface is going to rest on top of a million dimensional weight space, and no one really knows what's happening there. So these are all very intuitive, very heuristic explanations which don't kind of try to give you a sense of what might be happening, but honestly speaking, no one really knows what is happening.
And sir, if some weights are outliers, then which algorithm should we use?
No idea. So these are. What do you mean by outliers? In what sense are they outliers? Are they labeled? Are they
Like
noises?
sir, all the weights are like in 2 digits, but some weight are very high. So it will, if we take the gradient, then those weight will take over the.
Okay, you mean outliers? You mean weights that are having different scales? Is that what you're?
Yes, sir. Like
weights having different scales. That is bound to happen, right? So, especially if you have we discussed the vanishing gradient problem in the lectures, or is that pending? Is that yet to be done?
So it will be in the week 5 first lecture.
Okay. So yeah, so that is a problem that's going to be there, right? So you are going to have different scales. That is what leads to these valleys, right? So you have a weight that is extremely sensitive in this direction, and you have a weight that is you have a loss function that's sensitive, more sensitive in this direction than this direction, right? So that problem is going to be there. So how to solve that problem? That's what they use. That's why they propose momentum. But yeah, I don't know how much momentum helps. But yeah, the solution to that is this one, as far as theory is concerned. Right. So Adam incorporates momentum, right? If you remember, have you gone to Adam? So like the week 5 optimizers.
sir, I have gone through them, but all the algorithms mixed up.
Yeah. So that brings me to this point, right? So what should you learn from the exam point of view? You don't need to learn every single. So please do learn, but what should you focus on? These are the algorithms, right? So optimizers in DL, you have to know gradient descent, mini batch gradient descent, stochastic gradient descent, and you must know what momentum does. You must know what nag does, and then next week, right? So you need to know what ADA grad is, right? So ADA grad, what is it? What is RMS prop? And what is ADAM? Okay, so there are other algorithms that are there, but you don't need to really go through them in that detail. Okay, so the reason I'm saying that, like focusing only on this is This is what our standard textbooks are also doing. So if you look at the standard textbooks, I've gone through 2 textbooks which are which I suggested as reading material, right? So they go through only these optimizers. Okay, that's one reason. And in practice, you typically end up using Adam and SGD, right? So you seldom go beyond these 2 unless there is some real reason for trying out something else. Usually Adam is like the workhorse for all deep learning tasks, right? So if you don't know what to do, you pick up Adam. So for exam also, please concentrate on knowing these thoroughly, right? So GD, momentum, mini batch, NAC, metagrad, RMS, prop, Adam. So these are your adaptive optimizers, so learning optimizers with adaptive learning rates, right? And these are your these lay the groundwork, right? So these are your basic optimizers. Okay, and out of these, the most important concept that Adam will use is momentum, right? Momentum and some concepts from Adagrad and RMS prop, right? So yeah, so any other questions? If not, that's all. That is all I had prepared for this today's session.
So, sir, have you recorded this lecture? It's a beautiful lecture.
Yeah, I have recorded. So I have streamed also. So
sir, one after reading this much many algorithm, okay, sir, I am somehow is now fumbling with the perceptron algorithm. Is it natural or?
Sorry, you are sorry.
Fumbling with the basic perceptron algorithm. I somehow found that I am not able to forget the perceptron algorithm.
Okay. But aren't they? Okay, so maybe that is natural because both of them are iterative in nature, and that is also kind of gradient descent. If you think about it, perceptron also is in fact, perceptron can be thought of as doing stochastic gradient descent with a batch size of 1. So you can think of perceptron that way. Are you aware of that? Maybe that will, yeah. So perceptron is there, right? So you have, so you if you define the loss this way, so if you define the perceptron loss as, what is the perceptron's loss? It's the number of misclassifications, right? So you have indicator function of W transpose Xi. So if it is
Yi.
So that should be greater than 0. So if it is less than 0, then you are doing an error. You are performing, sorry, you are making some error, right? So this is 1. So when is this 1? This is, so this is the error function, right? So if this is less than 0, then this is 1 if the perceptron makes an error and 0 otherwise. Correct? So where I'm using the following label convention. So use y equal to 1 for positive. This is not what we use in our course. It's used in MLT, but this is easier. So I'm using this. So this is your perceptron error function, right? In fact, this is the error on one data point. If you submit for your entire data set, this is your error. This is what you will get. Okay, this is error or loss function. So now you can think of, okay, so there is a nice way of expressing this, right? So this is what? This is max of W transpose Xi Yi, comma 0 with a negative sign. Okay, so that's the error. Okay, this is max of W transpose xi yi. Okay, so if there is an error, what will happen? This is this comma 0, right? So if W transpose xi and yi are in the same direction, then let me know if this makes sense. So if W transpose xi and yi are in the same direction, if W transpose xi and yi are in the same direction, their product will be positive, right? Which means this quantity will be negative. So, and therefore the error will be 0. So 0 if there is no error or correct classification. Otherwise, the error will be minus W transpose xi yi. Wait, is this clear? This is.
But why you make minus here?
See, because error should be positive, right? So I want a positive error. So what does that mean? So the farther apart this is from the boundary, the higher the error. Okay, so meaning if you draw this, right? If you draw this, it will become clear. So if you have your axis like this, and you have your decision boundary, say something like this, and your W is, let's say, perpendicular to the boundary, and you have your data point, let's say it's a positive data point. So now, yeah, so W transpose xi for this data point will be negative. Is that correct? Because the angle is obtuse, right? So W transpose xi will be negative for this. Now consider another data point. Now W transpose xi will be negative for this also, but it will be larger because this is an even more serious mistake. Right? So that's what the error measures. So I'm defining error this way for misclassifications. So the moment I define the error this way, I can now run stochastic gradient descent, right? So for that, what do I need? I need the gradient of the loss function. Let's take the gradient for a single data point. So I'll take this for the ith data point. So that's actually gradient of this big quantity, right? Max of minus W transpose xi yi. So the max is for the whole thing, right? This is the quantity whose gradient I need to compute. So I'm going to compute this in a piecewise manner. So if you take this, so this is what I have. I had a gradient symbol before this. So if it's correct, then this function is 0. Gradient is also 0. If it is a mistake, then the gradient will be what? W transpose xi, if you take derivative with respect to W, you will be left with xi. Okay, so this is the gradient. Now you apply the gradient descent update rule. So Wt plus 1 is Wt minus eta. Eta you keep it as 1. So learning rate times the gradient. Gradient is minus xi ya. So what does this become? This becomes Wt plus 1 is Wt plus xi ya, right? So this is exactly the perceptron update rule. Okay. So whenever you have a mistake, so whenever W misclassifies xi yi, then you update W as the following. Right. So this is your perceptron update rule. So what we have mentioned is, what we have derived is perceptron can be viewed as stochastic gradient descent, meaning batch size is 1, applied on the above loss function, right? So the loss function, I think this is called hinge loss or something. I'm not.
So I want to ask something. So this y where you have written otherwise, is it of the true label or the predicted one?
True label, true label.
Okay, sir.
Okay, so that is the connection between perceptron learning algorithm and the stochastic gradient descent, right? So you can, there is a link between the two. All right, any other questions?
No, sir, but okay, I will go through the video. Probably I don't understand fully the perceptron, but I will go through the video and I'll ask in the disclosure.
Sure, yeah. Okay, then. Yeah, so thanks for joining and yeah.
Okay, bye.
Sir,
Yeah.
I have some queries actually.
Okay.
Regarding these slides that you have provided, in those slides, lecture 5, page number 41, can you please show the formula of momentum based gradient descent there? I have some problems relating to understanding between the formulation and the analogy between the model that was provided in the course. Actually, what model that was written in the actually slides given. Between these two things, I cannot actually relate to it.
Which one? The course slides, right?
Yes, sir. Momentum-based gradient descent formulations have. Can you please show that part? Page number 41 of lecture 5.
41. Okay.
I'm talking about the slide lectures that has been provided to in our portal actually for.
Yeah. Okay, so yeah, maybe I'll just stop streaming.
Yeah.